So we will talk about this interest point detector. As I said in the previous lecture, we talked about the edge detection. So we are looking at the edges, and here we are interested in interest points, and good example of interest point are corners, because there are lots of edges here, but there's got only one corner. There are three main components that we want to detect these interest points, identify them as shown in the right picture. These are the circles. These can be potentially interest points. Then we want to describe these interest points with some feature vector, and this is a feature vector or descriptor for this particular interest point. It is high dimensional feature vector, like a SIFT would be 128 dimensional feature vector. This is the descriptor of that another interest point. And then ultimately we want to be able to use these descriptor interest point to match two images. So that's the main point, that in order to analyze images or a video, we want to relate one image with other image, and to relate that we have to find something interesting here, and hopefully can find same thing here, and then we can match that this point matches with this point matches with that. Okay, so that's what is shown here in this image, that these are the potential matches, which are the correct one, which human can easily match, but computer has to do that automatically. So now once we can do that, it has lots of applications. We can do tracking, because in the video we have several frames, and we want to track an object from frame to frame. So we want to say, given a point in an object in this frame, where did it go in the frame 2, frame 3, frame 4. So we have these correspondences, and we have a track of that. And there can be several objects. We want to come up with the tracks of all the objects, like cars, people, bicycles, and so on. And of course we can do stereo matching, because we have stereo 2 images, and we can do calibration, we can do segmentation, and we can recognize objects. These can be features of the objects, and we can do 3D reconstruction, even robot navigation. The robot, when it's moving, it's sensing the environment and needs to analyze its motion and know where it is. So these are the basic building blocks, the features, interest points, which are used in lots of these applications. And also indexing and retrieval of images. If you have lots of images, you want to retrieve, say, given an image, can find me the similar image, then we have to do some matching, and matching is using, say, interest points. So our goal is that we want these interest points which are repeatable, which means we detect the interest point in one image and the other image of same scene, then we should be able to detect similar interest point in other image, then we can match. Okay, and here's an example. Now the left image, we have these interest points which we are detecting, which are shown in the circles in blue one. On the right image, the interest point we detected, which are shown in red one, and there's a difficult, we cannot really match those because they are different places in the image. Okay, so we will have a hard time. So generally the descriptor role is that we want to determine this interest point matches with the other interest point in the image. We want to say what is the texture, what is the descriptor around that interest point locally, and if it matches this locally with that locally, then we say it's the same thing. Okay, and that's the example here. Suppose on one interest point, our local window is here. Now if these are the potential matches, then we want to say, well, does this look like that, does this look like that, and so on. And how do we do that? One way will be, we can look at the RGB value at each pixel. We have 3 values, red, green, blue, and we can match those. But those values are not really good because they are sensitive to noise. They have some, they vary with illumination and all those things. So we want to come up with some better descriptor which is not sensitive to those changes. And that's what the descriptor we are going to talk about. So it has to be invariant to geometric transformation, like depending on what viewpoint we look at, even though it's the same scene, and also the the photometric, which is the appearance due to lighting and due to the illumination condition. So that is the desired properties of a descriptor, and we are going to talk about that, what that descriptor should be. So given these two images, if you look at a small neighborhood around these, suppose around here it looks like that, and around here it looks like that, and around here it looks like that, and similarly this is the another image, and we have these descriptors. Now we want to detect those which we can match easily. So as you see that this kind of descriptor, this kind of appearance, it's very ambiguous because it can match anywhere. This is a problem here. This is also a problem because a flat, we will find something like that in many places. But this one is a little better because this is a more unique kind of profile here, which we can match easily. So so detection is one important thing, and in general the question we want to ask, what we mean by interest point. So one thing we want to say, we want to match something, there's a texture, there is some we can express what is in that area which can help us distinguish. If there's nothing, is a flat, then it's very difficult to distinguish. Okay, so other way to look at it is that, well, we look at the direction of an edge, and if the direction of an edge or a boundary changes drastically, as shown here, then that may be interesting point, and that's normally a corner. There's corner, you have an edge, and then all of a sudden the edge direction changes, and that is a corner. Or it may be intersection of two lines, and that may be also interest points. Okay, so if you have a synthetic image where you have fixed gray levels, then these are the corner points, and it's very easy to identify. Wherever there's change, these is obvious corners and so on. Here's intersection of two lines and so on. And this is a real image where there are some genuine corners on the windows and so on, walls, but there are lots of corners around in the trees where there's a lot of texture. So properties of good interest point detector are that it can detect all true interest points. Okay, it's very similar to edge detection we talk about. There should not be false interest points, and should be well localized. It should occur, it should give us exactly same pixel location where it is occurring. It should not be delocalized. And it should be robust to noise, and it should be efficient. We can do it quickly. So the one way will be that we will look at the brightness or appearance. You will hear these words: brightness, appearance, gray levels, color. These are the same kind of thing, same information. Okay, and as I've said in this course, you will hear again and again the derivative of images, because that is the one which is providing a lot of information. The change, the first derivative, the gradient, the Laplacian, and all those things we will see again and again, and that's is interesting. Other thing you will see again and again, a Gaussian filter, and that's the kind of theme of this course. So so other ways they will get the edges, get the fitter lines, and you look at if they are intersecting lines or there is a change in direction. So in this first you will detect the edges. You will look at the curvature, how the direction is changing, how the curvature is changing. Curvature is rate of change of direction, and so these are the general ideas here. So we talk about specific interest point detector, which is pretty popular and works pretty well. Lots of people use it, and was proposed in 1988 by a researcher in England called Harris. So what he did is that you look at the corner point and look at that, we can actually recognize this corner point by looking at a small window, and if we shift that small window, then it give us a large change around that point. Okay, so that's kind of intuitive description of that. And here's an example. So here's one situation where you are looking at in this area, and we keep shifting the window, and as you see, there's no change because all is constant. So this is actually not interest point. It's a flat region. Another example here we are going to move these window around the edge, and again it doesn't change much. It looks very similar. So this is not also a potential interest point. And if you look at here, now here the change is significant because different part of the image around that corner is exposed, and that is a good interest point which we want to use. Okay, so now the reason the corner or interest point is good because it does not have aperture problem. As I told you that you can look at the scene by a soda straw where you're looking at a very small region, then there's always ambiguity most of the time. But if you look at the whole thing, then there's no ambiguity. So the idea is that there is one image which is red and other is a yellow. If you see the whole thing, then you of course say that, well, this point should correspond to this one, and this point should correspond to this one, and this point should correspond to this one. It's easy because you are saying the whole thing. But if you look at the very small area, then there's aperture problem because there's ambiguity. So here is the ambiguity because if you take this small region which is shown a circle in the yellow one and try to match that with the red one, it can equally match with this, equally match with this, because it's exactly same. Where you are looking at small neighborhood, local neighborhood. So that is called aperture problem. That is called that you are looking at local neighborhood and it's creating problem. It's ambiguous. It's not giving you a unique match. Here the corner does not have a aperture problem because it is very unique. This kind of profile will not match with this one here, or this one here, or this one here. This is a unique place where they are intersecting. So also if it is a flat region, again this thing can match with anywhere in the other object. So that is also a problem. So that's why we prefer the corner. So the way we are going to drive this, so the question is, so we are convinced that given an image, we can detect these interest point or corner point. And the question is, how do we detect that? Now, one can come up with some heuristics, say, well, okay, scan the image, do this, do that, and which may work, which may not work. But how do we mathematically derive what we want to detect? And that's what we're going to talk about that. And we are going to use this notion of correlation, as we have talked about before, that we have, say, F and H. F is the image and H is a kernel, and this should be H. And we can correlate that. We can find a correlation applying this mask as we have talked about before. So F here, there's H, and then we get the correlation of this. So what we are doing here, we are finding the pixel by pixel multiplication of these two, F and H, and if they are similar, this value will be high. If they are not, the similar value will be low, and that's what the correlation idea is. And we are doing this for this shift, which is for K and which is for I and J. So now there are two correlations. One is called the cross correlation, which is between two different functions or two different images. One is the F image, or other is the H image. They are two different, and so it's called cross correlation. Then other is called when we take the same one, we take the F and take another window, shifted window, and find the correlation pixel by pixel multiplication. It is called autocorrelation because we are doing with itself. The first one was with F with H. Okay, so these are two notions of autocorrelation, cross correlation. Okay, so another thing, yes.
For which cases is the first one? For which cases is the second one?
So this is a cross correlation, yes, and this is called autocorrelation. So the cross correlation means that these two have to be different. This and this cannot be same. Okay. Now this one, they are the same. So as I give you an example here, that as you see, we are multiplying f with h. These are different values. But now somehow we multiply f with f. So it is called the autocorrelation. We are finding a correlation with itself because f with f. But when you say f and h, we are finding cross. F is different from h. That's the idea. Okay. So now another notion is called SSD, sum of square differences. Okay, SSD, sum of square differences. It's very similar to the correlation. So here, instead of multiplying, we are subtracting. So we take the value of f and we go to h, so corresponding value we subtract. Then we square. Then we take next value, these are the loop here, and subtract the square and so on. Again, exactly same, those 9 values, if it's a 3 by 3 mass, we subtract corresponding pixels, square them, sum them up, it's called SSD, sum of square differences. Okay? So the interesting thing is that sum of square differences is very related to correlation. Okay? So if we want to find how similar f with h, then sum of square differences should be small as possible. Ideally it should be 0 if they're exactly same. Okay? Now, which means we want to minimize this SST. Now in the correlation we are multiplying, so if we want to say if they are similar, then we have to maximize that. Okay? So this is the, if we take the SST, the definition, we take the f, we subtract from h, square it. Now let's expand that. So this will become f square minus 2fh plus h square. That's your, the expression of a minus b whole square, a square minus 2ab plus b square. Okay? Now when we want to find the how similar f and h are, then this term does not contribute anything because this is only telling us about f. This term also does not contribute anything about how similar they are. The only term contributes is this one, which is a multiplication. Okay? So therefore we can actually remove these two terms, f square and h square. So now we are left with this term, and for SSD we want to minimize. So I'm putting here. And so this is a minus. Now let's say we remove the minus sign, then instead of minimizing this, we will maximize this. So right? As a negative. So therefore, now as you see, this actually is a correlation. Okay? So that is what we have, the correlation like that. So which means in the correlation, we multiply and we maximize. In SSD, we subtract and then minimize. So they are related. So that's what you need to know. Okay, given this background, so we will go back to the Harris interest point detector and look at that. We want to look at the SST essentially. We want to look at the change in intensity for a displacement UV. And that is the image. We want to detect the interest point. And this is the intensity at xy, and this is shifted by UV, and we want to subtract and square. It's the same exactly SST. Okay? So, so this in a way is doing similar to autocorrelation, and that's what we were calling earlier autocorrelation. Okay? So now we want to do this for every possible displacement UV. That's why this is a function of UV. Now in addition to this, we will apply this weight as we talked about on Tuesday. We'll apply a weight to each pixel, and these weights can be uniform, equally weighted, or we can apply the Gaussian weight, okay, to give more importance to pixels which are close to the XY as compared to the other pixels which are further away. So that's fine. So now we look at this again, the correlation surface or the SST. So we can look at the different points. So this is a point around a texture area, And this, if you blow that up, the small window, it looks like that. Now if you do this surface for each possible UV, we compute the value and we plot it, and that plot looks like that, which means it has a nice unique minimum. And if we take another pixel here, now here it's mostly flat, and this is what's shown here, and that UV surface will look like this, which does not provide you much information. It's very ambiguous. And if you take one around the house here, then it will provide you, this is the profile here, or like that. This is again aperture problem because there's no unique minima there. So therefore we will kind of prefer this kind of thing, which will be a profile of an interest point or a corner. Okay? And we are going to do this by using Taylor's, using the correlation. So there is another notion which I want to explain very quickly. It's called Taylor series. So if you have any function f, which is a function of one dimension, say, we can represent that function in terms of the value of function at the point and the derivative of that function at that point. First derivative, second derivative, third derivative. That's called Taylor series. Taylor was a famous mathematician who said, well, let's approximate a function by this. It's a very simple idea, and it's a very, very useful idea. So here we are saying f of x can be approximated by f of a, the first derivative of f evaluated a and x minus a, second derivative of f with respect to the x and evaluated 2 and x minus 2 square and so on. This is called Taylor series. So this is a better way to approximate a function. It will simplify a lot of things. Again, this thing you will encounter again and again in this course. So the idea is there are few key concepts which we will build on our discussion, and once they are clear, then I think you can do pretty well. And for the sake of completeness, I'm going to cover each and everything so that I don't assume that you know these things, even though you must have learned these in calculus and so on. Okay, so now getting back to the Harris, so we have this expression, and what we are going to do is we are going to find the Taylor series of this function, which is ix plus u, y plus v, and we will keep this as it is, and this function we are going to approximate it xy. So that's why first term it ixy, then it will be a first derivative of this I with respect to x. So this is a function of 2 dimension. So differentiate with respect to x first, then differentiate with respect to y, and then this term as we have, which will be x plus u minus x, because we are doing at the xy, so that we got u here, and from here y plus v minus y, so we'll get v, and then this is exactly same. So this is pretty simple approximation of that I x plus u y plus v by Taylor series, just first order term, which means only you have first derivative with respect to x and y. So now the interesting thing will happen, because you can, as you see, this and this is same. We can cancel it. Okay? So that's what we are going to do. So w will remain same here. Then this will cancel. This is u ix plus v iy, and whole thing is square. Okay? So that's good. Then we are going to rearrange this. We are going to essentially break this. So this can be broken in 2 vectors. One is ix, iy, and then another vector uv. So if you multiply this with that, you will get this. Because this is 1 by 2, and this is 2 by 1. You will get 1 by 1. So that's, kind of, you have these 2 vectors. Then we are going to do further is that we are going to now expand this, since it's a square thing. So w will remain here. So we'll have uv ix. Then we will have the transpose of this, because we are multiplying. So we will have ix iy. Transpose of this is ix iy, and then transpose of this will be uv. It's multiplication of vector a multiplication of vector with matrix. So that's what we have now. After that, then we have weight again here, and then we have we have IXIY, which is shown here, and then we have UV here, and we are going to take this UV a little bit outside here. We'll just group these two together with W, and that is what we have here. So since it's a scalar, so we can move this in, that's no problem. And this is our vector, which is here.
UV is constant?
Huh?
UV is constant?
No, UV is just a vector. So see that this is a vector, this is a vector, this vector, and all this thing. And this is the scalar. Yes? So a scalar we can bring in here, and we will define this as some matrix. It's not a constant. Just we are going to group them and call that as a matrix. Okay, so just for convenience. Okay, so that's what we have. So we have W, IXIY, this thing, this three terms, we'll call the matrix M. So because this is the 2 by 1 and 1 by 2, this will become 2 by 2 matrix, and each element will multiply by W, and then we have our UV here, which is UV here. Now this is a vector, and this is a transpose of vector here, so that's fine. So we have a UV, and this whole thing is matrix M and UV. So that's where we are now. Okay, so now we and of course as you saw here, that M matrix, this matrix, essentially a 2 by 2 matrix, as we said, which will be, the first term will be Ix multiplied by Ix square, and then Ix multiplied by Iy, the second term in that column, then Iy multiplied by Ix, second column, and then Iy multiplied by Iy square. And that is your M matrix, which is shown here. Okay? And so that here you can see again that we are ending up again derivatives of images. The derivative of the x, derivative of the y, and Ix square, Iy square, IXIY, and all those things. So that's pretty interesting that everything reduces to derivatives. Okay, so so this is actually, if you look at this is the equation of an ellipse. Okay, and M is a covariance matrix. Now we are going to take this matrix M and look at its eigenvalues. Again, this is a concept which is very easy, very intuitive, but I'm going to explain what we mean by that. Okay, so let me actually do that. We can come back. So eigenvectors and eigenvalues. It's a very simple concept, very useful. So eigenvector x of any matrix A is a special vector. When you multiply that vector x with A, you get the vector back and some scalar multiplying. So it will be like this. I take a matrix A, multiply with x, I get the vector back x and some scalar lambda. So x is called eigenvector, lambda is called eigenvalue. That's a very simple idea. Okay, so then to find the eigenvalues and eigenvectors of matrix, what you do, you take a matrix A and do minus lambda I is the identity matrix, and find a determinant of that equal to 0. So that will solve this, it will give you eigenvalues of a matrix. Okay, and so example is here. Suppose A is a matrix like that. Then these are the eigenvalues of this matrix. So 3 by 3 matrix will have 3 eigenvalues. So 7, 3, and minus 1, these are eigenvalues. And these are the corresponding eigenvectors. So corresponding eigenvector 7 is 1, 4, 4, and then corresponding to 3 is 1, 2, 0, and so on. So every eigenvalue will have eigenvector corresponding to that. Because as you say, x plus x is equal to lambda x. So that lambda is the eigenvalue, x is eigenvector. So which means that it tells you how you do it. You take the matrix A, lambda, put the identity matrix, subtract these and find the determinant of that. So if you subtract, this will become -1, and this multiplied by lambda will become minus lambda, and all these terms become again 3 by 3, and determinant of this will become this term and multiply by this and subtract, and you know this how to do that. And this one, you remove this column, this row, multiply these to 0, and then third one will be remove this row and this column, and then take this one be 0, and so on. So then you will have these, and the root of these are lambda is equal -1, lambda is equal 3, and lambda is equal 7. It's a pretty simple linear system, and it gives you 3 eigenvalues. Now what you do, you take the eigenvalue and find the corresponding eigenvector, because you apply the definition of the eigenvector that says that ax should be equal to lambda x, and that's what I have here, because I took the x common, so I got identity here. Okay, so this is my A, this is identity, this is what I want to find out. So I add these up, I get this one, and this is the linear system, 3 by 3 linear system, 3 equations, 3 unknowns. I can find out x1, x2, x3, and I'll find out x1 can be 1, x2 is 0, x3 is 0. So this is essentially eigenvector corresponding to the eigenvalue -1. And if you take that 1, multiply with the corresponding matrix, you will get the eigenvalue back, and you can verify that. So that's a notion of the eigenvector, eigenvalue, determinant, and all these things, which you should know. It's a pretty simple idea, but very useful. So let's now get back to what we were doing before, and I think, let me see if I can continue here. Yeah, okay, I need to go back to that slides. So you'll have to edit this thing. Okay, so as we said, we were here, EUV, and we have a matrix M, and this matrix M is defined like this. And the way we are going to do is we are going to look at the eigenvalues of this matrix M, and now you know how to find eigenvalues. Okay, so this, actually is the equation of an ellipse, which looks like that. It has these major axes and minor axes, and they depend on these eigenvalues. One direction tells you the maximum change, other tells you the minimum change, and that's what these maximum minimum eigenvalues are. So we did that, and so now we want to essentially look at these eigenvalues and decide that whether that point should be an interest point or not, whether that should point be a corner or not. Okay, so we started with the definition that we want to look at the sum of square differences, that the window has to be different, and we want to find out that shift we do UV, where that function is minimized, maximized, so that we find the best location for that interest point. And we found out that we can rely on these eigenvalues of that matrix M, which actually have the derivative of that page, Ix, Iy, Ix square, Ix, Iy square, and Ix, Iy. So now if you look at the different values of lambda 1, lambda 2, these two eigenvalues, then what's going to happen, that if these lambda 1, lambda v are very small or close to 0, then that will be the flat region. If you take a flat region, the window, and compute the M matrix and go through all this, find eigenvalues, you will have, it will be around here. Okay, now the corners will be around this region. So lambda 1, lambda 2 are large, and they are maybe close, and E will increase in all directions. Then we have these other regions where lambda 1 is greater than lambda 2, so that is an edge, it's one direction. And this is also an edge where lambda 2 is greater than lambda 1, that will be another direction of edge. So that is kind of tells you that what are these lambda 1, lambda 2, which are the eigenvalues of the that matrix M, are providing information which you can use. Okay, so the measure of the cornerness is in terms of lambda 1, lambda 2. So this Harris, he defined this factor, the variable R, which is the lambda 1, lambda 2 product of them and sum of them and some constant K. So this is called R. And this is also another way to define R, because the determinant of M matrix is essentially a product of its eigenvalues. Okay, and trace is a sum of its eigenvalues. So and that's what is shown here. So therefore, another way to look at that, instead of looking at two values, lambda 1, lambda 2, we can look at just R, which captures the sum and product of these lambda 1, lambda 2. So if R is small, the magnitude of R is small, then it's a flat. If R is positive, R is negative, then it's H, and if R is positive, greater than 0, some value, then it is a corner. So that is kind of criteria we can use. That R depends on eigenvalues of M. R is large for a corner, R is negative with large magnitude for an H, and R is small for a flat region.
What's small and large?
Yeah, so that again, the same question as you asked last time, that you have to have some notion of what is small, what large. So then you will have to say normalize. Say, well, largest is 100 in terms of percentage and small is 0, so you can apply a threshold there. Huh?
Like a threshold?
Threshold, that's right. Okay? So everything will end up with threshold. So it's better to normalize between 0 and 100 than you say what's percentage, Say, well, I want very good corners, 90%, I want lots of corners, maybe 70%, so on. So that's subjective. Okay, so suppose this is an image. There are these two images of this animal, and so if you compute these, apply this Harris corner detector, you will get values like this, and then you can apply a threshold, and these will be where the R is greater than the threshold, and so we'll take only points which are local maxima. That's another thing. If there are many points on the same pixel which are greater than, R is higher, then maybe same corner but it's been detected many times. So you want to do maxima suppression, which means if it is a local maxima, just select that. If it's not local maxima, don't select that. Okay. So if the pixel is greater than its neighbors, then it's a local maxima. So then you will get fewer of these, and you'll have more cleaner output. So now, so there are different other versions of the same Harris detector, and it just that matters on this R value, So R value, there's a Triggs method which says, well, let's just simplify, just look at the lambda 1 and lambda 2 with some constant. Look at how different they are, what's the difference, and that should be the measure. There's Zaleski has done harmonic mean, which says take the product, divide by the sum, and use this as a metric. Zaleski is the author who wrote a book. You can access that online. And this is another one, Shi and Tamasi. They say, well, just look at the first eigenvalue. So now you can compare these different criteria, and this is shown again, lambda 1 and lambda 2, and Harris is this one, then this is Zaleski, and this is Shi and Tamasi. So it's telling you the region that, suppose if you use the Shi and Tamasi, it's just it will be around this region where this is fixed on, here. And if you use the harmonic mean, it's this curve shown here, and then Harris. So you get a similar output, but some little differences. and the people have compared that, and there's comparison. But I think any one of these is reasonable. So then, in a nutshell, if you want to write a program for computing the Harris corners, then steps are very simple. Given an image, you will first compute the Ix and Iy, the derivatives, derivative with respect to x and derivative with respect to y. And then, as you saw in the M matrix, we had 3 types of terms. It's a symmetric matrix. We had Ix square, Iy square on the diagonal. Then we have Ix, Iy. Okay, so we have 3 terms. So given these derivatives at each pixel, Ix, Iy, you compute 3 matrices. One is Ix square, basically you square the Ix, and Iy square, and then multiply Ix, Iy. So that's, and these matrices basically the images, same size as the image. Then you want to apply that window thing. So the best way to apply window is just do the convolution with the Gaussian, as we talked about, of all those 3 images. Okay? Then you compute the matrix M from there, then for each pixel, then from there to compute eigenvalues, compute R, and they apply threshold. And so in MATLAB, it's very easy to compute the eigenvalues. Just EIG is a function which will give you eigenvalues and eigenvectors of a matrix. Okay, and then you find local maximum and apply some threshold, then detect interest point. So that is the Harris corner detector. And I think there's very nice description in this book. You can get this in section 4.1.1. Any questions? Yeah.
The previous slide.
Mm-hmm.
I didn't understand the second one. Can you do the images?
This one? Yeah. So see, you want at every pixel you want to compute this M matrix. M matrix, as you saw, it has 3 terms: the Ix square, Iy square on the diagonal, and Ix Iy and Ix Iy. So one way will be that you create 3 images. In the first image, the value should be Ix square, because you already computed Ix square, every pixel Ix square. Another image Iy square. Third image Ix Iy. And then use that to compute M for each pixel, find eigenvalues and all this thing. Okay, more questions? Go ahead. You have a question? No.
These operations are made only in the Windows, right?
Yeah, so see that now what you're going to do is you are going to compute this for all the all the pixels in the image. Then when you compute this or the M matrix, and as you saw here before, let's go there, that it is in a window. So you'll have to do this thing in a window when you compute the R matrix. Here, see, so you will do in a small window where you are applying the Gaussian filter. Yeah. But since you are going to use these derivatives anyway, so you just compute once for all the pixels. Then you look at each pixel, and then you will do this kind of summation. Okay, let's see. Any other question? More questions? So I think the main point here is that you have to understand that always we have to work with images, and we are trying to extract some useful information from images. In this case, we want to find interest points. So we have a mathematical definition what the interest point is, and we explain that, and then we came up with some algorithm in those steps I described to compute the interest point. And it seems all that ends up with is in terms of the derivatives of the image and the filter, the Gaussian filter. And there is a threshold, there is the local maxima, and there's this window operation. So these are kind of key things. Once you understand clearly, then I think you can follow that pretty well. You have a question? So the right now we have covered just the detector. Even though we started talking about the descriptor, and we haven't talked about the descriptor yet. So I think if you are curious to try this out, if I were you, I'll just go home and write this program. It's a very simple program in MATLAB, since you already know how to find the derivatives given an image, and you can see what you get. It'll be a pretty short program. To do that, you will will be able to verify what you have done. Okay, so any questions before I go to the next one? Today actually I will end a little earlier because I have to leave. I have to meet some visitor, so we'll have 15 more minutes. Any other question, comment? So far you guys are happy? It's going well? It's clear? And how about the video? Videos is okay? Is useful? Okay. So let's maybe get started with the next thing.